Our next speaker is going to be Vladimir Lifschitz. And Vladimir has been a colleague of John at Stanford during the 80s, 90s. So Vladimir.
I was fortunate to work closely with John for about 6 years in the 1980s. And one of the issues that he was interested in at that time is what he called the common sense law of inertia. And this idea is related to actions, such as moving an object to a different location or toggling a light switch, for instance. And according to this common sense law of inertia, whatever you know about the state of affairs before an action is executed can be presumed by default to hold after the action as well. And formalizing this default would solve the difficulty known in AI as the frame problem. Reasoning involving defaults is non-monotonic, and John proposed a solution to the frame problem based on his method of non-monotonic reasoning called circumscription. And then something unpleasant happened. Two researchers from Yale University came up with a counterexample which showed that John's solution was incorrect. This counterexample involved the actions of loading a gun and shooting, and it became known as the Yale shooting scenario. And 20 years later, their paper received the AAAI Classic Paper Award. But that was not all. Even assuming that this difficulty with Yale shooting example could be resolved, there was yet another difficulty. Reasoning is notoriously difficult to automate, and the presence of defaults adds yet another level of complexity. So one could ask, was there any hope that this common sense law of inertia would ever become part of usable software? So John's method was technically unsound, probably unimplementable, and also it seemed unnecessary because other researchers, Niels is one of them, came up with alternative approaches to the frame problem that did not require non-monotonic reasoning. So there were all indications that John's idea just wouldn't fly. But history showed otherwise. It was destined to fly, and in fact to fly quite high in outer space. I'd like to say a few words about a program written many years later by a group of computer scientists who continued John's work on non-monotonic reasoning in collaboration with engineers from United Space Alliance, the company responsible for the day-to-day operation of the space shuttle fleet. The program was called the RCS Advisor. The RCS, or the Reaction Control System, was a system aboard the shuttle that was used to change its position in space. And the RCS Advisor was needed to verify the reliability of the design of the RCS in the sense of the possibility of using it even in the case of multiple failures when several components malfunction simultaneously. And this program included a formalization of the common sense law of inertia very much along the lines of John's original proposal. So how was this possible given all the difficulties that I mentioned before? And first of all, what about the Yale shooting problem? Well, the answer to this question is that simple ways to fix the mistakes in John's original formalization had been found. Ideas came partly from the experience with the programming language Prolog, and the solutions that we have now look so simple and natural that it's not easy to explain to our students today why this Yale shooting scenario attracted so much attention 25 years ago. But what about the difficulty of implementing non-monotonic reasoning? We have now something that was not available back in the 1980s. Fast satisfiability solvers for propositional logic. Propositional logic is monotonic, but the ideas used in the design of set solvers can be applied to non-monotonic languages as well, and these languages have a lot in common with the language of circumscription that John invented, and the common sense law of inertia can be expressed in these languages, and that's how the RCS advisor operates. But why didn't the designers of the RCS advisor use simpler monotonic solutions to the frame problem, since those were available? They had good reasons for that. The RCS was a complicated system, and effects of action, such as flipping a switch, had to be described in two steps. First, you would specify the simple direct effect of the action. You flip the switch, the state of the switch changes. And then the program also contained a number of rules describing the operation of the RCS that would make all the other effects of the action consequences of this direct effect. And if you want to describe the effects of an action in this two-step manner, then you need to use a non-monotonic solution to the frame problem. So what this example shows is that John's work on non-monotonic reasoning was not only interesting philosophy and beautiful mathematics, but it also gave us computer science with serious applications. Thank you.
Thank you. I remember Vladimir once wrote a paper, something like, someday we will have non-monotonic reasoning, or something like that.